Okay, let me from the last class we talked about synthesis and just started metal complexes. As I told you that when the metal is, so today we will elaborate on metal complexes and give you some examples, okay, some real examples, although in cartoon form. What happens? Oops, nitrogen is there. This cartoon I will write the compound only once, and then I will say that this is the cartoon, this is the compound. Okay. So, this is the cartoon form. Cartoon form. What happens? Let us see, this is ortho, but you can get meta also. Okay. When you take meta, meta is little bit large, elongated and very rigid. Now, what is the characteristics of these compounds? If I put a transition metal ion, I told you cobalt or copper, they will be here. Cobalt or copper, they all stay here, and this metal is bonded to 4 nitrogens, 1, 2, 3 and then bridged 4 nitrogens, such that this place is empty. This coordination, anything can coordinate. You know that copper likes 5 coordinates, 6 coordinates. Similarly, cobalt also likes higher coordinates. That means, there is a provision for something else to come here, all right. And when something else comes here in a meta, something else comes, especially we have isolated with meta, like if you use with copper, if you use say potassium thiocyanate, KSCN, okay. If you use potassium thiocyanate here, first we write copper perchlorate with this cryptand, we get copper inside, and copper inside is very stable, like we had macrocyclic effect, here is because of this cryptand, it is called cryptid effect. So, cryptid effect means it is a very stable, both thermodynamic and kinetic stability is very high for these systems. So, the metal ion is very happy here and is bound, it cannot be moved very easily. Okay. When I say very easily, you have to take it, understand it, anything can be moved with proper reagents, but this is, I am saying that difficult to move, all right. Now, if I put, and perchlorate should be here outside, perchlorate. Now, if I put potassium thiocyanate, thiocyanate again goes, because I said that the geometry is such that geometry is something like this. If I write this 3 nitrogen and this fourth one, then metal sits above this. Metal binds to this metal will bind to this 3 and then 4 nitrogens, okay, like this. This metal binds, and so that this site is empty. If we put potassium thiocyanate, now thiocyanate binds. Thiocyanate binds to copper through nitrogens. Okay. So, it binds nitrogen, carbon and sulfur. Do not worry about the bonding, okay, double bond, single bond, like that, do not worry about that. So, it binds like that, and it binds, actually it comes away from it, away from the cavity, it is outside, it comes outside. Why? Because it likes to avoid these hydrophobic aromatic spacers. So, it comes like that. However, this can be moved again, and as I told you, we could make use of this facility, that copper is held tightly and this side is empty, this place is empty. So, what will happen? It makes a large number of organic transformations at room temperature. Oxidation of olefinic and benzylic substrates can be done, okay, both by copper and cobalt 2 cryptate. So, as I told you, this can be done pH, will get, I am writing few only, pH, okay, quantitative transformation from olefin to epoxides, and so this is benzylic, and sometimes another one. This it can go pH, is about 80%, more than 80%. And some more examples I will give you. If you take compounds of this type, the product will be okay, about 70%. Remember, what are the conditions in each case? Room temperature, and it takes up oxygen from air in presence of isobutyraldehyde as the sacrificial agent at room temperature. With these cobalt or copper cryptate, we can get this kind of oxidation products. You can get epoxides or you can get this carbonyl compounds, all right. So, and because copper or cobalt are tightly held, I am not going through mechanism right now, okay, but there is no need to go through mechanism right now, but you know that this kind of reactions can go very easily. There are bunch of reactions. We did about 15 substrates were available in the laboratory, and we got this kind of results. Okay, so this is a mononuclear cryptate. I did not mention another. Now it is a dinuclear cryptate. Let me show you a dinuclear cryptate and its ability. This is a dinuclear cryptate. I am writing now. Okay. This aromatic I am unable to make properly. Let me write like this. I should not be writing like this, but for this. Let me write nicely. Okay. And then yeah. So, this cryptane was synthesized and it forms with cobalt a dinuclear. Cobalt OH, with water it forms like this, certain conditions, okay? And then cobalt here, another cobalt here. With a basic, under basic condition, it can form like this, and one cobalt here and a cobalt hydroxy bridged. This compound, not only this, if we do not put under neutral condition, then hydroxy will not come. Then these two cobalt, this compound can take up carbon dioxide from air and can make carbonate complexes, carbon, oxygen, oxygen complexes. So, when oxygen and oxygen, these complexes it can form. So, they are very important compounds, and they are all, because these compounds are very stable, the cobalt is very tightly bound. So, you can play with it. This particular compound that I have done here, this hydroxy, okay, after carbonate comes is hydroxy. This hydroxy, I will tell you, the react is what happens, it exhibits highly efficient photocatalytic reduction. Photocatalytic reduction. reduction of carbon dioxide. I told you that it can accept carbon dioxide. So, this will go and carbon dioxide will bind here of carbon dioxide to carbon monoxide, and photocatalytic means you use a 45 nanometer LED lamp, 450 nanometer light, LED light, for 450 nanometer LED light with a very small intensity, and carbon dioxide can be reduced to carbon monoxide, and the yield can be as high as 98%. You know the problem of carbon dioxide, global warming and all that. So, people are trying to reduce carbon dioxide to react carbon dioxide to other substances, okay, carbon monoxide, and then it will react. Carbon monoxide is more reactive than carbon dioxide. So, carbon monoxide can react with suitable reagents, and it can be that way carbon dioxide can be removed. So, carbon dioxide can be this way can be modified to different other materials. So, this catalysis, these are homogeneous catalysis, because in one whole thing is soluble in acetonitrile and water, okay, and these are very highly efficient photocatalytic reducing agents. Why highly efficient? Because the cobalt is very tightly held. Cobalt is very tightly held here. Okay. Cobalt is very tightly held. Okay. So, cobalt is very tightly held here. Cobalt is very tightly held through this, as I told you, 4 nitrogens on either side, and their distance is such that a carbon dioxide can easily fit. That is why it has a very strong tendency to fit, and that can be oxidized to carbon monoxide in presence of a 450 nanometer LED light, LED lamp, and with a light intensity of 100 light, small intensity, and the yield reaches as high as 98%. Okay. So, it is very important, where one of the centers, this center acts as a catalytic center, and this center will be assisting, okay, in the catalysis. So, two metal ions can work synergistically to bring out catalysis. So, there are many other methods, many other systems like that. Okay. Then I will show you examples of trinuclear examples, if I can find. Yeah, this is one example where I find trinuclear. Okay. So, trinuclear will be like this. This one I can put cartoon, does not matter, but after that I have to put this is a phenanthrolene moiety. So, I am writing this, yeah, maybe I should write it inside. Nitrogen is inside, it can go inside, rotate. Okay. And then this is strain. So, this tris phenanthrolene derivative, this one it can put 3 silvers, one silver here, another silver here and third silver here. So, 3 metal ions can be put inside and more than 3 are not known yet. However, so therefore, these cryptands can accept 3 metal ions, some cryptands can accept 2 metal ions whose distance can be varied via ligand design, and then again cryptand with smaller cavities can accept only 1 metal ion. So, mononuclear cryptid, dinuclear cryptid and trinuclear cryptids are known. Then I will tell you another example of the cascade complex, which I did not mention, but I use so many. So, this is a cascade complex if suppose I have a mononuclear cryptand. Okay. Mononuclear cryptand and this a metal ion is here, a metal ion binds here with these 4 nitrogens, and then what happens? Then another thing binds, another group, maybe cyanide group will bind, or thiocyanate group I showed you, well let us say thiocyanate or cyanide. So, that means this is known as a special name called cascade complex. Cascade complexes. So, what is a cascade complex? The definition would be when a cryptid either mononuclear or dinuclear or trinuclear, if they bind to certain anions or neutral molecules, then the resultant complex will be called cascade complex. Okay. For example, it can bind a one water molecule also. Why NCS? It can bind water molecules also through, it can bind water molecules also, that will be another cascade complex. Oxygen, 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 nitrogen, okay. And water molecule can bind oxygen, hydrogen and hydrogen. This hydrogen can be hydrogen bonded, make many, we have synthesized some compounds like this. Okay. So, cascade complexes are also very important in catalysis. They can be used like the one with dicobalt cryptid we have found. So, therefore, what we have learned from cryptands, that cryptands can be of varied structures, and depending upon its structures, to sum up, that depending upon its structure, mononuclear, binuclear and trinuclear cryptids can be formed. In suitable circumstances, we can form cascade complexes, and We can put some neutral molecules are also there inside there, which I have not discussed, but I will discuss soon, maybe another time I will discuss. We can put neutral molecules, okay, or we can put anions, a chloride anion or a bromide anion depending upon the size we have put, or a nitrate anion can be put. They are also important. Per-renate and per-teknatate. Per-renate and per-teknatate are are obtained from nuclear fissile materials. So, there are cryptands people have made which specifically accepts per-teknatate, okay, and per-renate. These anions can be accepted, sequester, we call sequester from solutions, and they can be removed. So, this way they are very important in environmental issues also, all right. So, with this I stop this cryptand. Cryptand will be visiting many times, cryptand macrocycles will visit. So, in the next class I will be taking up another type of cryptand like molecules called cyclophanes. Thank you.